Okay, before we start, can I please get confirmation that you guys can hear me and see me? I'll be sharing my screen in 1 second. Actually, let me just allow you guys to talk. You should be able to. Okay, can you guys hear me and see me? I'll be sharing my screen in a second. Okay, perfect. That's great. Okay, so let's get started, right? Assalamu alaikum and good morning. Welcome back, guys, to grade 10 physics, okay, by Inspired Teens. Today we'll be continuing waves. I think we just have to finish up magnetism. Okay, I think we might have went through, I'm not sure if we completed like all of this, but you guys can tell me, we can go through it. And we'll start electrostatics, right? Yeah, so remember, please guys, if you have any questions, you can use the chat, you can use the Q&A. If for those of you who are on YouTube, you can use the YouTube chat. And remember that these notes will be sent to you guys afterwards, right? There's a Google Drive which it will be uploaded to, and the link to the Google Drive can be found in the group description in the WhatsApp group. Okay. So let us continue. So we were discussing the electromagnetic radiation spectrum. Okay, with the different types of electromagnetic radiations, radio. I don't think that was for everyone. I'm pretty sure some people still have to learn magnetism. It's not a long section, right? If anyone else knows whether it was taken out of their syllabus, please let me know. Does anyone know? Nobody? No one knows? Okay, what I'll do is I'll leave it out for today. You can always come back to it if there's a need to, if anyone still needs to go through it. But I'll leave it out for today, and like I said, we can always come back. We can always come back to it. We still do it. Okay, then we can go through it, no problem. Okay, but nevertheless, so can say again. Okay, so I was just asking. So somebody says that electromagnetism is, magnetism has been taken out of their syllabus. So I'm just trying to check if everyone has been informed that it has been taken out of the syllabus and that they're not doing it. Just to confirm, so that I know. So does anyone know? Is anyone aware of whether it has been taken out of the syllabus or not? If not, it's fine. Okay, let's just go through it, right? Let's just go through it just for the benefit of everyone. It's not a long section either way, right? If it's not in your syllabus, it's fine. Listen for interest. If it is, then you can benefit from it, right? So yes, we were busy discussing this. So we went through radio waves, microwaves, infrared radiation, visible light, right, which is what we see, UV rays, X-rays, gamma rays. Okay, so we went through the different advantages and disadvantages of each. okay, and the different usages and disadvantages. Okay, so let's go through this. Sound and electromagnetic waves. It's just basically a summary of what is above. I kept it in here because it's quite a nice summary, right? To summarize what's happening with regards to sound, okay? What's important with frequency and amplitude, what's important with echoes, okay? The distance to the wall and back, okay, is 2 times the distance that they generally give you, okay? And then electromagnetic radiation, okay, it gives us the basic explanation of what it is. Accelerating charges are the source of all electromagnetic radiation. They propagate as electric and magnetic fields, which are perpendicular to each other. The wave is propagated at a speed of 3 times 10 to the 8 meters per second in a vacuum. Okay, that is called c, the speed of light. We will be doing electrostatics. Does not need a medium to propagate through and can travel through a vacuum. This is electromagnetic radiation, right? Electromagnetic radiation behaves like a transverse wave when it propagates. Electromagnetic radiation behaves like a particle when it interacts with other materials, right? It has a wave nature and it has a particle nature. So from the wave nature, we utilize this formula, c is equal to f lambda. Wave speed is equal to the frequency times its wavelength, okay? As the frequency increases, the wavelength decreases, right? Remember, we discussed the relationship between frequency and wavelength. It's important for us to understand, all right? So then we have, so we did this last week. Yeah, I'm just revising sort of what we did last week. I just want to brush through the summary, okay? Then we have the frequency and wavelength relationship in this electromagnetic table. Particle nature, okay, we discussed the formula, okay, E is equal to HF, right? Remember, E is equal to HF can also be written as E is equal to C over lambda. So this is, the top one is energy written in terms of frequency, the bottom one is energy written in terms of wavelength, right? Energy, electromagnetic radiation transfers energy in packets called photons. A photon is basically like an energy packet that transfers energy to particles of matter. It's like the unit of measurement for energy. The greater the energy of the photon, the greater the frequency and its penetrating ability. So yes, that's important. Like, it's good to go through the summary because they summarize everything in like bulleted form, everything in one place, and it will make sense. Okay, let's go through magnetism. Okay, so a magnetic field is a region in space where another magnet or a ferromagnet material will experience a non-contact force. Okay. Okay, so I think the basic understanding of what a magnet is and what the word magnetic means, I think we all have that concept, right? So a magnetic field, okay, is a magnetic field is created by a magnet, okay? It has these invisible forces that have the ability to attract, okay, metals and other magnets as well, okay? It's a non-contact force. It will exert a force on another object without being in contact with it. Okay, so a non-contact force is the force exerted on an object without touching the object, okay, just like a magnetic force. Okay, a magnet, an object with a pair of opposite poles called north and south. Magnets can be made from ferromagnetic materials, which are materials which are strongly attracted by magnets and are easily magnetized. Okay, common ferromagnet materials include iron, cobalt, nickel, and their alloys. Okay, when two magnets are brought close together, right, like poles repel each other and unlike poles attract. So when we talk about like poles, we talk about north and north. Like if you bring north and north together or south and south together. When you bring unlike poles, we have north and south and north, right, whatever, right? But basically north and south. So unlike poles, they attract each other. They will move towards each other. The like poles would repel each other. Even if a magnet is cut into little pieces, it will form smaller magnets, each with their own north and south poles. So as we can see, even if a magnet, which has a north and a south pole, is broken into 3 different pieces, it will form its own poles. Okay. Right, let's talk about magnetic field lines. Magnetic field lines are imaginary lines around a magnet indicating the direction and the strength of the magnetic field surrounding the magnet. Iron filings on a paper can be used to indicate the field line. So I'm not sure if you've ever, so when are you writing exams? You tell me, when are you writing exams? It depends on your school. Different schools have different dates. Most people are around the first week of March. Okay. If you've ever seen, I don't know if you guys have ever seen a video where iron filings, like little small thin filings of iron, okay, are placed around a magnet. And as soon as they are placed around a magnet, they automatically create the shape, okay, that shows us the field. I'll link a YouTube video where you guys can see it. It automatically it creates the pattern of the magnetic field around it. Okay. So the field lines occur inside the magnet and three-dimensionally outside it. They come out of the magnet near the south pole and enter near the, they come out of the magnet near the north pole and enter near the south pole, again forming a loop. Here we go. So these are basically what the magnetic field lines look like. So when we say they're imaginary, meaning you can't see them, okay? They're not like a physical thing that you can see coming out of every magnet, okay? It is an invisible force, okay, an imaginary line, okay, created by this magnet. We will be covering magnetism and electrostatics. Okay, so bar magnet, right? So as you can see, the magnetic field lines are drawn around a single bar magnet, and they indicate the direction out of north and into south. Okay, that's really important for us to note. So properties of magnetic field lines, they are imaginary lines, okay? They are continuous, okay? They are three-dimensional in all the different dimensions of the magnet. They never touch each other and they never cross. Arrows indicate the direction of the field from north to south and are more concentrated at the poles where the field is stronger. So basically, the lines are closer together at the poles, okay, as can be seen here, as opposed to this empty space. Okay, just other types of fields that you get in physics. A magnetic field, an area in which a magnetic material experiences a magnetic force. An electric field is an area in which an electric charge experiences an electric force. Gravitational field, an area in which a mass experiences a gravitational force. Let's look at the attraction between like poles and the repulsion between, the attraction between unlike poles and the repulsion between like poles. So when we look at two magnets placed next to each other, motion in one direction, I'm not sure if we'll be able to get that. I think it's regarded as a term 2 topic. Are you guys done with electric circuits? Because no. The person that asked to do motion in one dimension. Are you done with electric circuits already? Most of you should be on electrostatics and then starting with electric circuits. That's my guess. Let me message them. Okay, yeah. Okay, so most people are electric circuits / electrostatics. Okay, so attraction between unlike poles. Okay, so we can see two separate magnets, right? These two separate magnets have their own north and south poles. And then you can see that because they are unlike poles, remember, so they have their own magnetic fields respectively, right? So these are their own coming out of north, going into south, as well as this magnet, right? Out of north into south, out of north into south. But then there's also these forces that are between these two unlike poles, south and north pole. These are the attraction forces between these magnets. Okay, so the magnets, they have their own magnetic field lines, and they also have these attractive forces between one another, okay, because north and south. Then we have repulsion between like poles. So when we place south and south, or alternatively, if we have to have north and north, okay, you can see that these are pushing away from each other. Okay, so they're pushing away from each other. It's a repulsion force. Okay, so whereas these are attracting, okay, these are pushing away from each other. They are not touching each other. They are not going towards each other. They push each other away. Okay, so we can see south and south. So when asked to draw, okay, the repulsion between like poles, this is what you would draw. When asked to draw the attraction between unlike poles, this is what you would draw. Okay, you don't have to maybe draw so many field lines for the north to south and make them so big. But the main thing you need to show is firstly, field lines of each magnet traveling from north to south, as well as attraction in the unlike poles, field lines going from north to south in each magnet, and then as well as the repulsion, okay, from like poles. Okay, cool. Let's move on to this. Earth. Let's talk about Earth's magnetic field. Yes, chemistry will be done at some point. We will probably not this term because chemistry is not scheduled for this term. I believe it's scheduled for next term. Classes during the holidays, time will tell. Okay, let's not jump the gun for now. No problem. It's okay. I understand people do have questions. Okay, so Earth's magnetic field, right? The Earth behaves as if it has a giant bar magnet running through it, with its magnetic field looping around the Earth. The arrow of the compass is the north pole of the compass and points towards magnetic north pole of Earth. In reality, the north pole of Earth is actually the south pole of the imaginary magnet through the Earth. The point in the northern hemisphere where the Earth's axis meets the surface of the Earth is the geographical or true north. A compass will not point to this, but rather to the magnetic north pole, which is actually the south pole of the imaginary magnet through Earth. The angle between the true north pole and the magnetic north pole is called an angle of declination. Geographical north pole point in the northern hemisphere where the rotation axis of the Earth meets the surface. Magnetic north pole, the point where the magnetic field line of the Earth. Okay, that made no sense, I'm guessing. Okay, but let's explain that through a diagram in order to understand that. Okay, because there was just a bunch of words that were just confusing. So let's look at the Earth. Okay, now let's look at this simple diagram. So we have this axis. Okay, now true north, or sorry, not true north, geographical north point. Okay, geography, that is geography, the subject when we talk about the study, okay, of the Earth, right? They say that, where is it? Geographical north point is the point in the northern hemisphere where the rotational axis meets the Earth's surface. So this is the axis upon which the Earth rotates. Okay, that is the point upon which the Earth rotates. So that is why we refer to this point, okay, where this axis meets the surface. We refer to this as geographical north. Okay, it's almost like the top of Earth, if you want to call it that. That's the imaginary line upon which the axis, the Earth, rotates. So we call this geographical north. So geographically speaking, like it's there, you see, like literally, if you want to call it the most top point of the Earth, we call that the North Pole right there. Okay, the top of your globe, basically. Okay, that is the geographical north, okay, or true north. Okay, however, right, where is it? Okay, so it says that the Earth behaves as if it has a giant bar magnet through it, right? So the Earth is basically one big magnetic field. The Earth has one big magnetic field, okay? However, the placement of that magnetic field is not in line, okay, with true north and true south. So the magnet is not parallel to the rotational axis of the Earth. The magnet, if it had, it doesn't actually have a magnet, it behaves as if it had a magnet. So let's just pretend, okay, it has a magnet inside Earth, right? It is slightly slanted. Okay, this is the direction of Earth's magnet. Okay, it's slightly slanted to the left. As you can see, even here. Okay, this magnet inside of Earth, okay, is slightly slanted. So, you know, when you use a compass, okay, the compass uses the Earth's magnetic field. So the compass actually does not point to geographical north. It points towards magnetic north. Now, magnetic north pole, okay, is slightly to the left of geographical North Pole. So magnetic North Pole on Earth, okay, is somewhere here. This is magnetic North Pole. So your compass actually does not point to geographical North Pole. It points slightly to the left. So as you can see, if we have to focus on Earth itself, right, geographic North is on top, somewhere there, right? However, magnetic North is somewhere there. It's actually like in northern Canada, somewhere. It's a certain distance, okay, away from geographical North. Okay, I hope that makes sense. So you get geographical North, and that's magnetic North. Why is it magnetic North? It's because the Earth's the Earth's magnetic field, okay, is at that point. Its south pole is technically at that point. Now, where did it say that? Okay, the point in the reality, the North Pole of Earth is actually the South Pole of the imaginary magnet through Earth. That's a key thing to understand. So remember, opposites attract, okay? So within Earth, it's actually the South Pole that's there. And at the bottom is the North Pole, okay? So the magnetic fields behave, okay, as if there was a bar magnet through the center of Earth, okay? And at magnetic North Pole, okay, is where the south part of the magnet is, and the north part of the magnet is at the bottom. Okay, we are just going through magnetic fields just for the benefit of the doubt. For many people, it has been taken out. So it's not a long session. After Earth's magnetic field, we're done, basically. And we'll start electrostatics. Okay, so as you can see, this is what the field lines would look like. It's almost as if we have a magnetic bar in the center of Earth, okay? And the field lines go from north to south, okay? Imaginary magnetic field lines, okay? Geographical North is the actual northern part of the Earth. It's where the rotational axis meets the surface of the Earth. However, the Earth has its own electromagnetic field. It has its own magnet, if you will, within it. It's not actually a magnet, okay, but it behaves as if it has a magnet, where the south pole of that magnet is actually closer to the North Pole. We call that magnetic North Pole, and that's actually where your compass points. Okay, now where is that information? This here, the angle between the true North Pole and magnetic North Pole is called the angle of declination. Okay, so as you can see, it can be represented by this angle here. This is the angle of declination. Okay, so I hope that makes sense. Magnetic phenomena. The sun releases particles, mainly electrons and protons, which travel outwards in all directions at speeds of up to 900 meters per second. More particles are released during a solar storm called the coronal mass ejection. When these particles come close to the Earth, the magnetosphere protects the Earth by deflecting most of the particles. However, some penetrate the magnetosphere and are pulled towards our north and south poles. They enter the upper atmosphere at high speeds and collide with nitrogen and oxygen molecules, causing them to glow with the different colors. These are known as the northern lights, or the aurora borealis, or whatever. Okay, or the southern lights, aurora australis. Okay, so that's how the northern lights are formed. That's quite interesting. Right, now electrostatics, before everyone panics. Let us start. Okay, so firstly, we're going to be going through methods by which a neutral object can become charged. The first is through friction, also known as triboelectric charging. Okay, we're going to try and speed through the theory so that we can get to the calculations. Okay, also known as triboelectric charging. When you rub two objects together, such as a glass rod and a woolen cloth, electrons are transferred from one object to another, okay, depending on which materials are used. Okay, no problem. The one object loses electrons and the other gains electrons. Okay, so let's look at a diagrammatical example of glass rods and woolen cloth. So we have a neutral rod and a neutral cloth, right? When the two are rubbed together, it creates friction. What then happens is that the electrons migrate from the rod to the cloth. Electrons migrate from the rod to the cloth. Once that happens, we will see an excess of electrons in the cloth and a negative amount of electrons, so more protons. So the electrons were at a loss of electrons in the rod. So initially, the rod had 3 electrons. Now it has 1 because it donated its 2 to the cloth. So the cloth went from 5 to 7. Okay. The protons did not change, however. They remained constant in all. Remember, neutral. What is a neutral object? A neutral object is when the amount of electrons and protons are equal. Okay, positive and negative. Okay, let's look at the example of the PVC rod and woolen cloth. Initially, both are neutral. Thereafter, electrons are transferred when they are rubbed together to create friction. Electrons are transferred from the cloth to the rod. The electrons are lost from the cloth, went from 5 to 2, and the electrons are gained in the rod. Let's look at contact. Same charge, I think, same charge 4. When a charged conductor, oh, you mean for neutral. Okay, electrons and protons are equal. It's an object that has an equal amount of electrons and equal amount of protons. Contact. When a charged conductor touches an identical neutral conductor, electrons are transferred to make the charge on the conductors equal. Positive conductor touches a neutral conductor. Negative charges are transferred from neutral to positive. Okay. So one key important thing to note here is that the more negative charge always transfers electrons. When it comes to contact. Okay, so let's look at these two. These are two charges. The one has a 2,8 coulomb charge. The other one has a neutral charge. All right. Between the two, how do you know which one is transferred to? Okay, I'm explaining that now. How do you know which one of the electrons are transferred to? We're going through that now. So the more negative one always donates. More negative always transfers electrons. Okay, that's how you know which one's going to transfer electrons. So between the 2,8 coulomb charge and the 0 coulomb neutral charge, which one is more negative? What is more negative between 2.8 and 0? What's more negative between 2.8 and 0? Somebody tell me. Okay, most of you are correct indeed. We are saying 0. The reason for that is it's basically looking for the one that's more left on the number line. Okay, the one that's more left on the number line is more negative. Okay. So in this case, if we look at the 2,8 coulomb charge and a 0 coulomb charge, which is neutral, right? The more negative one is 0 coulombs. Okay, when they are made to touch, okay, essentially what happens is, I don't know if you've ever done this experiment in like grade 7, okay, where they make you put your hand on something warm, okay. So for example, if you had to put your hand on the desk, right, I have a wooden desk in front of me, and if I put my hand on this wooden desk, initially the desk feels cold. Okay, initially the desk feels cold. That's because my hand, I'm warm-blooded, and my hand is warmer than the desk initially. Okay, but I'm keeping my hand on the desk. You can do the same if you like, right? And as I keep my hand longer on this desk, okay, the desk is starting to become less cold. Okay, it's starting to, its temperature is starting to match that of my hand more or less. Okay, until I keep it, if I keep it there for a minute or two, I won't be able to tell the temperature difference between my hand and that specific part of the desk. That's because what happens is the heat, okay, always is going to transfer from the hot object to the cold object. So heat is being transferred from your hand to the desk, okay, until they have the same amount of heat. Okay, so a similar thing applies when it comes to charge. Okay, so the more negative one is always going to donate. And what happens is because one has extra electrons, one has less electrons, when they touch, the electrons transfer from more electrons to less electrons until they become the same charge. Okay, so like in this case, when the neutral charge, okay, touched the 2,8 charge, what happened was it transferred. Okay, so don't worry about this amount for now. We'll learn how to do the calculations, but it transfers the negative charge, the electrons, to the 2,8 because it basically wants to be equal. Until what happens? Until when they are separated, okay, both objects have the same charge. When they're separated, both objects have the same charge. What if both objects warm? No transferring. So when you talk about warm, they both objects are the same temperature. Both objects are warm. Remember, in that case, whichever one is warmer is going to transfer to the less warm one. Okay. However, if they were both the exact same temperature, then there'll be no change. There'll be no exchange of heat. Okay. But remember, when it comes to charges, it's not heat, it's charges. Okay. The heat example was just to understand the concept, okay, of these electrons transferring over. So with like how your desk, how your hand is eventually going to be the same temperature as the desk, like they meet in the middle, basically. Okay, your hand transfers enough heat over till you guys are the two objects have the same temperature. So similarly with charge, electrons are transferred over until they are the same. Yes, exactly, correct. You would say 2,8 plus 0 divided by 2. So yes, that's what happens, right? And when we separate them, as you can see, they now have the same charge. So negative conductor touches a neutral conductor. Negative charges are transferred from negative to neutral. In this case, between negative 4,6 and 0, negative 4,6 is, of course, more negative. So that is the one that's going to donate or transfer the electrons. And eventually you get negative 2,3, negative 2,3 coulombs. Again, we will do the calculation shortly. Let's talk about induction, a method of charging whereby objects do not touch one another. A neutral electroscope is charged by induction. So we have in the neutral electroscope, and a positive rod is placed nearby. Okay. Now, when the positive rod is placed nearby, the electroscope is polarized with the top negatively charged and the bottom positively charged. Okay. So in the top, on the top, there's an excess of negative charges, and at the bottom, there's an excess of positive charges. Okay, remember, here's the description. The positive rod is brought close to a neutral electroscope. Electrons are attracted to the positive rod, positively charged. Remember, opposites attract. So the positively charged leaves and repel each other. So basically, yes, when the positive rod is placed on the top of this electroscope, it attracts all the electrons. And the positive rod is placed on top, it attracts all the electrons, and the protons are now stuck at the bottom. And the electrons are attracted when so after the electrons are attracted to the positive rod, those positively charged, now in the bottom we have positively charged particles, and they repel each other because they are like charges, and they eventually leave. Okay, then we have a neutral electroscope. Okay, a negative rod is brought close to a neutral electroscope. Okay, so obviously it's a negative rod. Okay, happen is it's going to attract all the positive charges and all they're going to repel. So electroscope is polarized with top positively charged and the bottom negatively charged. Why? Because of this negative rod that was placed near this electroscope, it repelled all of the other negative charges. So thereafter, what happens? Electroscope is earthed, allowing extra electrons to come towards the rod, and a semi-permanent charge is created. So as you can see, because of the excess amount of electrons at the bottom, okay, the electrons repel each other and they too leave the electroscope. Okay, a really, really good video demonstration okay, is this link here. If it doesn't work, what I'll do is I'll send the link in the WhatsApp group as well. Okay, then you guys can go through it. It's a really nice video. Please can you explain the concept of polarization? So polarization is taking place here, right? So what happens in polarization? Essentially, remember the electroscope is neutral, okay? So it has an equal amount of positive charges and it has an equal amount of negative charges. What we mean when we say it was polarized is when within that neutral sphere, or in this case, it's an electroscope, polarization is the separation of the pole. So basically, creating, so in this specific case, remember the positive rod, let's call this the top. Let's call this the bottom. Initially, we can see an equal spread of electrons and protons. However, what happens when the positive rod is placed at the top of this electroscope? We can see that all these negative charges have moved to the top to sort of, because they are attracted by this positive rod. And all the positive charges at the bottom, all the positive charges are now at the bottom. Not all, but most of the positive charges. And we find an excess of positive charges at the bottom with no negative charges. So that creates the polarization when we have positive, negative. The top is negative heavy, okay, meaning it has more negative charges, and the bottom has more positive charges. The polarization, creating the positively charged and negatively charged, and it temporarily charged. Why temporarily? Because the rod is placed nearby, and if the rod is moved away, the electroscope would return to the again. Okay, does that make sense? Okay, so polarization. Okay, again, please make use of this video. It's a diagram experiment carried out that basically explains this process, but like the person actually does the experiment. Okay, so it will make sense. Always electrons. Well, let's work if the rod is neutral. If the rod is neutral. No, I'm not sure. I don't think anything will affect. I'm just trying to think. If the neutral rod is charged. For now, learn about the positive and negative, right? I don't think it will be affected. The electroscope, there won't be polarization if a neutral rod is placed near the electroscope. Okay? So no. Okay, let's move on to electrostatic calculations. Okay, so we'll be dealing with objects touching each other and calculations with regards to it, right? Let's look at charge, okay? So when we talk about a charge, okay, we either talk about an excess amount of electrons or an excess amount of protons, okay? Electrons are negatively charged while protons are positively charged, right? Now, we look at our first formula, okay? N is equal to charge. Okay, so basically in terms of variables, N is equal to Q over QE. Let me get my notes open. Okay, N is equal to Q over QE, okay, where Q is the charge and QE is the charge of a single electron. Okay, by the way, it is a given formula in the formula sheet. Okay, and in this case, okay, N, so let's write out what it is. N is number of electrons. So if you're calculating like the amount of electrons, like, okay, 5 electrons, 6 million electrons, 7 billion electrons, 6 trillion electrons. This is the charge in coulombs. We can almost say it is the total charge. And this guy is the charge of a single electron. Can we use Q is equal to N times Q? Yes, correct, because that would just be this rearranged. So it would be, if you take QE to the other side, QE is written as Q as well sometimes. It would be N times Q of QE, just rearranged. Okay, so we have a number of electrons, so it makes sense, right? If you want to calculate how many electrons there are, you know the total charge, you know the charge of a single electron, you take the total charge divided by the charge of a single electron, it's going to give you the amount of electrons that they are. Okay, so when we face with a question like this, how many excess electrons make this charge? How many excess electrons make this charge? So in this case, what you would do is utilize this formula where N is the number of electrons. So this is what we want to calculate, number of electrons, N, right? Q is the charge. What charge do we use? We use the charge of the actual, of this charge. We use the value, the magnitude of that charge, which is -6. So -6, okay. Units, I have the units written down. We have microcoulombs, we have nanocoulombs, we have picocoulombs with their conversions, times 10 to the -3, times 10 to the -6, times 10 to the -9, times 10 to the -12. Okay, so you need to know these. So therefore, the reason you need to know it is because it converts milli, micro, nano, and picocoulombs to coulombs respectively. In this case, sorry, in this section, the SI unit for charge is coulombs. So we have to convert to coulombs. So in this case, it's given as NC, which is nanocoulombs. To convert it to coulombs, we times by 10 to the -9 with nano. Okay, so times 10 to the -9. This is the charge. You actually use the charge, use the value of this of the charge you're working with, right? QE is a constant which you can find in the formula sheet. It is 1,6 times 10 to the -19. Now, this constant QE, you can either use negative or positive. When do you use what? When do you use which one? When your top value is a negative, your bottom value should also be a negative. When if your top value is positive, your bottom value is going to be positive as well. The reason for that is, remember, we are calculating the number of electrons. If you are going to the shop to buy a certain number of apples, can you come back with -9 apples? It's not possible, right? The number of something cannot be negative, right? So that's why you will match the sign on the top to the sign at the bottom, and then you'll always get a positive answer. And here, the number of electrons actually in this, sorry, they say how many excess electrons make this charge. The excess electrons that make this charge is 3,75 times 10 to the 10. Well, this also works for multiplication. What do you mean by multiplication? Yes, correct. I think you're talking about when you rearrange the formula. Yes, you'd use negative and negative and positive and positive. Okay, let's go through some concepts and then we can do the questions. All materials contain positive charges, protons, and negative charges called electrons. Okay, a neutral object has an equal number of protons and electrons and has no net charge. A positively charged object has lost electrons. We call it electron deficit. Okay, a negatively charged object has gained electrons, which is excess of electrons. A charged object can also be attracted to a neutral conductor. Okay, because of the movement of charges in that conductor. A charged object can also be attracted to an insulator because of the movement of polarized molecules present in an insulator. Charged object exerts forces on each other when brought close together. Like charges exert repulsive forces on each other. Opposite charges exert attractive forces on each other. Can you explain again? Okay, we have a good question. Why can't you just say that it has 6 excess electrons? Okay, because this -6 nanocoulombs is not an electron. It's not indicating electrons. It is indicating the charge. -6 electrons is indicating the charge. So we say, okay, it has -6 nanocoulombs more charge than a neutral object. Okay, so we cannot just say, okay, it has 6 excess electrons because this -6 nanocoulombs is the charge. So that's what this formula basically helps us to convert. It converts the charge to the amount of electrons. Does that make sense? Okay, because this is not the unit for electrons. Okay, it's charge. And then this formula helps us to convert from that charge, dividing by that, to get the number of electrons. Number of electrons has no unit, okay, because it's like 5 electrons, or in this case, 3.75 times 10 to the 10 electrons. This here is a charge. So it has -6 excess charge, okay, but not electrons. We utilize this formula to convert it to electrons. Okay, so we said that like charges repel and opposite charges attract. Oh, sorry. Okay, so let's look at this, the principle of conservation of charge. Okay, this is important. So let's look at the definition. The principle of conservation of charge states that the net charge of an isolated system remains constant during any physical process. Example, when identical objects with different charges touch, charges will be transferred between conductors. The two conductors will then have equal charge. Okay, so it's basically saying that no charge is lost, even if they have to come into contact. Okay, the charge will be transferred from one to another, not just completely lost. Okay, so an example is that two identical charges on insulated stands, 5, what is this? M is microcoulombs and -9 microcoulombs respectively. Okay, they meant to touch each other and move apart again. Determine the new charge on each, and B, the amount of charge transferred, and C, the amount of electrons transferred, right? So when we look at A, it says the new charge on each. Okay, when we look at A, it says the new charge, sorry, when we look at A, it says the new charge on each, right? So what is happening, okay, if we have to draw this scenario, we have two insulated stands. Okay, we have two charges, completely separate initially. Okay, one of these has a charge of +5 microcoulombs, and the second has a charge of -6 microcoulombs. So initially they are separated. They are then brought into contact. In the second scenario, second half, they are made to touch each other. Okay, don't worry about the size. The size really doesn't matter. Okay, it's just magnitude that's important. So they are made to touch. Let's actually just make them the same size. Peace of mind. Okay, so they are made to touch, okay, and then they moved apart. So they were made to touch, okay, and then back to scenario number 1, where they are moved apart. Okay, so this is just what the scenario looks like pictorially. It is -9. They did say -9. Okay, now these formulas are important to us. Q new, okay, helps us to calculate the new charge on each after contact. Q new after contact. Okay, so initially we had 5 microcoulombs and -9 microcoulombs. MC stands for microcoulombs. All the units are here. Sorry, not micro. I keep saying micro. Milli. Here's it here. Millicoulombs. So millicoulombs, microcoulombs, nanocoulombs, picocoulombs. Okay. So we have 5 millicoulombs, positive, and -5 millicoulombs. They want us to calculate the new charge on each. That was the first question. A, determine the new charge on each. Why? Because remember, when they are made to touch each other, they are in contact with one another, right? They are in contact with one another. And when they touch each other, electrons are transferred from the more negative to the less negative. and they transfer electrons until they are equal in charge, and then they are separated. So we can simply utilize this formula to do the calculation. Q1 plus Q2 over 2. Q is a charge. So first charge is positive 5 plus. Now you can choose to convert it to coulombs in the start or in the end. Okay, I would suggest it in the start, get it done and over with. 5 times 10 to the negative 3. Why am I saying times 10 to the negative 3? Because whenever I'm dealing with millicoulombs, I need to multiply by 10 to the negative 3 to get coulombs, and coulombs is the SI unit for this section. Plus, what is Q2? Negative 9 millicoulombs. Negative 9 times 10 to the negative 3 divided by 2. When we do this calculation, we get negative 4. No. Yeah, we get negative 4. Let me just. Confirm. No, we get negative 2. Oh, because we have to divide by 2, yes. So when we do the calculation, we get negative 2 times 10 to the negative 3. This is Q nu. So what is this exactly? It is the new charge on each, meaning the new charge of each sphere after contact and separation. So basically, okay, the new charge of each is now negative 2 millicoulombs and negative 2 millicoulombs. How come it becomes times 10 to the negative 3? So why do you have to convert it if they already gave it as MC? Okay, so there's two ways you could do this. You don't have to convert it. You could just say 5 plus minus 9 divided by 2, because they are both in millicoulombs. Okay, so if they are both in the same unit, you don't have to convert it. Okay, provided that your final answer has to have coulomb. So you convert it in the end. Why does it become times 10 to the negative 3? Because whenever we deal with these units, we have to convert it to coulombs by multiplying it by one of these. So if it's millicoulombs, you have to multiply it by 10 to the negative 3 to convert it to coulombs. Okay, so in this specific case, you're going to get an answer of negative 2. Then you have to say negative 2 millicoulombs. Alternatively, you're going to say negative 2 times, so instead of millicoulombs, I'm saying times 10 to the negative 3. These are the same answer. Okay. It's good habit to convert it early. Okay, in grade 11 and 12, you're going to have to convert it because you're going to learn formulas that only take in coulombs. Okay, sorry, so this is actually coulombs. Millicoulombs or coulombs. So the Q nu is negative 2 times 10 to the negative 3. Alternatively, negative 2 millicoulombs. These are the same thing. Okay, so now each one has a charge of negative 2 millicoulombs. Or instead of this, let's do someone tell me. I label this A and I label this B. In which directions are electrons transferred, from A to B or B to A? Okay, we have an A to B, but the rest are B to A. So B to A is correct, okay, because it's always from more negative to less negative. Okay, so that's why A to B is incorrect for the person that said A to B. You need to move from more negative to less negative. So from the negative 9 to the positive 5. Okay, so not A to B, it's actually B to A, because more negative to the less negative, always. Okay, so electrons are being transferred in that direction until they are separated, and now they have that charge. Okay, let's make a little bit of space. Okay, let's look at the next question. So that was the new charge on each. They said calculate the amount of charge transferred. So how much charge was transferred from the old charge to the new charge. So this is delta Q, also an important formula. Delta Q is equal to Q final minus Q initial. Okay, so Q final is the new charge on each, okay, and Q initial is the original charge before contact. Now you can choose, they say here you can choose, you can use either of the original charges in the step. So remember our original charges were 9, -9, and 5. So delta Q in this case is going to be Q final minus Q initial, where our Q final was -2. So if we're going to leave it as millicoulombs, we can write it as -2. If we're going to convert it to coulombs, you're going to say -2 times 10 to the -3. Minus, what is the Q initial? So the initial Q is 5 and 9, -9. You'll get the same answer, and I'll show you why. Let's choose 5, right? Here I'm going to get an answer of -2 minus 5. I get -7 millicoulombs. That's delta Q. If I go ahead and I do -2 minus -9, I get delta Q as positive 7 millicoulombs. Now, what's the difference, right? Remember here, I used the 5 initial, and here I used the -9 initial. Okay, let's compare the two. The 5 and the 9, we know that the 9 donates. So the 9, when it's donating its electrons, it's actually becoming more positively charged, right? It's losing its negative charges. So the 9 millicoulombs donates electrons to the 5. The 9 actually is losing electrons, so it's becoming more positive. Okay, and while the 5, positive 5, this one is becoming more negative because it is receiving electrons. Okay, and that's why when we calculate the delta Q, the change in Q, for the 5, remember the 5 is gaining electrons, so it has a negative change actually. What about the -9? The -9 is losing electrons, so it has a positive change. So it doesn't matter which initial you use, you're still going to get the same answer, just one is negative, one is positive. Okay, let's try and finish this. The number of electrons transferred, 1 second. Okay, the number of electrons transferred, they want to know the number of electrons transferred. So this whole time we were working with charge, new charge on each, amount of charge transferred, but now they want electrons. Okay, that's really simple. Okay, please keep in mind this is basically a formula that converts charge to electrons. That's what it is. It's a formula that converts charge to electrons or vice versa, meaning electrons to charge. So they want to know the number of electrons transferred. If you want to know the number of electrons in this formula, you need to know Q and you need to know QE. QE is obviously a constant, so we always know it, right? Now tell me, if I want to know the electrons transferred, firstly, I'm going to tell you, you need to know the charge transferred. So electrons transferred. I need to know the charge transferred. If I want to know the electrons transferred, I need to know the charge transferred. They need to match. Tell me, how much charge was transferred? How much charge was transferred during this interaction? 7 microcoulombs. Okay, so is it 7 or is it -7? All right, that's the thing. So how do we know how much charge was transferred? Here's the formula for it. Amount of charge transferred, delta Q is equal to Q final minus Q initial. New charge on each, okay, that we calculated utilizing that formula, and then we got the amount of charge transferred. Now, the amount of charge transferred, everyone is correct. When you could either say it's 7 or it's -7, right? Depending which charge you choose to decide from. If you're going to choose from the 5, it's going to be a negative charge transferred. And then if you're going to choose from the -9, it's going to be a positive charge transferred. So you can choose both. I'm going to start off by choosing the +7 or the -7. So the amount of charge transferred, now you see the important thing in this formula, people, in this formula, this has to be in coulombs, has to be in coulombs. You cannot substitute millicoulombs in this formula. I have no idea how to spell this word. It has to be in coulombs. So why you cannot use milli and micro and all of those. You're going to have to say 7 times 10 to the -3. It's equal to N, which is what they want me to calculate, the number of electrons, times QE. Now, QE, remember, is a constant from the formula sheet. If your charge is positive, your QE should also be positive. So we can do it like that. If you're going to choose the negative charge transferred, your QE that you're going to choose must be negative as well. Here we are getting an answer of 7 times 10 to the -3. QE is given in the formula sheet. I'm getting a number of electrons as 4,375 times 10 to the 16. Okay, there we go. Here's another example you could practice. We did one there. How many excess electrons make a charge? And the 3 different calculations that you required. Yes, it is indeed very late. I apologize for taking extra time. But yeah, okay, cool. So I'll see you guys next week where we will continue further. Did you times Q by QE? No, you divide. So because you take it over, N is equal to Q over QE. So you divide them. Okay, no problem. So I will see you guys then next week. All the best if you guys are writing in this week. Remember that. You guys are welcome. Yes, we will be able to revise it. We could try. I mean, let's see, right? It's tough. We're trying to do extra classes for you guys. It's just time. Okay. Okay, cool. I'm going to end it there. I'm extremely late for the next class. All the best, and let's